The ocean whispers its secrets to those who listen. Ready to uncover its mysteries? Beneath the surface of the serene blue lies a world in perpetual motion. Even in the calmest marina, the water is always moving, an endless dance choreographed by the sun and the moon. But there's more beneath this gentle facade. A hidden network of currents drives the ocean's flow, connecting the equator to the poles, shaping weather and sustaining life. These currents are the ocean's lifeblood, carrying nutrients and heat across vast distances. Invisible rivers traverse thousands of miles, weaving a delicate balance that influences our climate. They connect distant shores, shape coastlines, and remind us that nothing is truly still. As you gaze out at the ocean, remember, the water you see has traveled far, guided by unseen forces. The ocean never stops, never sleeps. It's the eternal movement, shaping our world in ways we're only beginning to understand.
Water is in constant motion, shaped by forces both subtle and immense. When we speak of currents, we are describing the flow of water, the way it moves and travels. You've seen it in everyday moments. Rainwater rushing down the street or a stream winding its way from high mountains to the valleys below. This movement, so simple yet profound, is driven by one of nature's most powerful forces, gravity. But the ocean is where the true majesty of currents unfolds. Here, the motion of water is stirred by forces beyond our immediate view. One of these is the rise and fall of the tides, driven by the gravitational pull of both the sun and the moon, a cosmic connection shaping the very flow of Earth's oceans. As the tide rises, water surges inland, creating what we call flood currents. When the tide retreats, water flows seaward once more. This is the ebb current. These tidal currents are unique among the many oceanic movements, for they follow a rhythm as ancient as the Earth itself. They can be predicted with astonishing accuracy, repeating their cycles like a heartbeat, steady and unyielding. The movement of our oceans is not only shaped by tides and gravity, but by another powerful force we all know: wind. Winds drive ocean currents that travel across the surface, creating vast streams of water that stretch for thousands of miles. These surface currents, often measured in meters per second or knots, are essential to life on Earth, transporting heat, nutrients, and life itself across the globe. One of the most famous of these surface currents is the Gulf Stream, a warm and swift Atlantic Ocean current. In this animation from NASA's Goddard Space Flight Center, we can see the Gulf Stream in action. This mighty current originates in the Gulf of Mexico, winding its way through the Straits of Florida, and then hugging the eastern coastline of the United States. As it flows north, the Gulf Stream veers eastward near 36° latitude, off the coast of North Carolina, before making its way toward northwest Europe. This journey is not only swift, but immense. The Gulf Stream transports water at an incredible rate, 4 billion cubic feet per second, through the narrow Florida Straits. This powerful current is a vital player in Earth's climate system, distributing warm water and influencing weather patterns across continents. A third factor that drives the movement of our oceans is the process of thermohaline circulation, a global conveyor belt powered by differences in water density. This circulation is driven by two key forces: temperature, or thermo, and salinity, or haline. In different parts of the ocean, variations in heat and salt content constantly alter the density of water, setting powerful currents in motion. Unlike surface currents propelled by wind or the swift tidal currents driven by gravity, thermohaline circulation occurs at both deep and shallow ocean levels and moves at a much slower pace. But despite its slow movement, this process is crucial for the distribution of heat, nutrients, and oxygen across the globe. Cold, salty water, dense and heavy, sinks to the depths of the ocean, while warmer, less salty water remains at the surface. Over time, this cold, dense water returns to the surface through a process known as upwelling, where wind-driven forces push surface water away, allowing deeper, nutrient-rich water to rise up and take its place. In following animation by NASA, we see one of the key regions where thermohaline circulation takes place: the North Atlantic Ocean, around Greenland, Iceland, and the North Sea. Here, warm surface water travels from the South Atlantic via the powerful Gulf Stream. Upon reaching the cold, polar waters, the denser water sinks, forming what we call the North Atlantic Deep Water Current. This deep current then returns south, completing a cycle that is vital to global ocean circulation. This continual influx of warm water into the polar regions keeps areas like Iceland and southern Greenland mostly free of sea ice throughout the year, despite their high latitude. The animation also highlights another critical element of global ocean circulation, the Antarctic Circumpolar Current. Near latitude 60 degrees south, the ocean flows unimpeded around the world, as there is no land in the way. Both surface and deep waters flow from west to east, encircling Antarctica in a powerful current that links all the world's oceans. This circumpolar flow allows the deep waters from the Atlantic to rise in the Indian and Pacific Oceans, while surface waters circulate back toward the Atlantic, completing the global cycle. As the animation begins, you can see how the density of surface water is represented by color. Dark regions mark the most dense waters, while lighter areas indicate less dense waters. This dynamic system, where heat and salt continuously shape ocean currents, influences not only marine life, but the climate systems that govern life on Earth.
We've explored the powerful forces that shape the movement of the ocean, the rise and fall of the tides, driven by the gravitational pull of the sun and moon, the relentless push of the wind, and the slow yet profound process of thermohaline circulation. These forces are immense, shaping not just the surface, but the very depths of the sea. But the story of ocean currents is far more complex than these individual forces alone. One fascinating phenomenon that adds even greater complexity to this vast, interconnected system is the Coriolis Effect. As our planet spins, it subtly influences the direction of ocean currents, bending their paths in ways that may not be immediately visible, but have a profound impact on how water moves across the globe. This invisible force, created by Earth's rotation, steers not just the winds, but entire oceans. Here's an easy way to think about Coriolis Effect. Imagine for a moment that the Earth is not rotating, completely still. You're standing at the equator, and someone else is standing near the North Pole. The Earth beneath your feet is stationary, so everything behaves just as you would expect. Now, if the person near the North Pole throws a ball straight toward you at the equator, the ball will travel in a perfectly straight line, just as you'd imagine. There's no twist, no curve, no deflection. The ball follows a direct path from point A to point B. In this still, motionless world, everything is simple and predictable. Now let's step into reality, where the Earth is constantly rotating beneath our feet. Imagine once again that you're standing at the equator, and someone near the North Pole throws a ball straight toward you. In reality, the ball still travels in a straight line, just as it was thrown. But here's where the Earth's rotation comes into play. As the Earth spins, the ball appears to curve from your point of view. It doesn't follow the direct path you'd expect in a non-rotating world. Instead, it veers off course. This apparent curving motion is what we call the Coriolis effect. It's not that the ball is really curving, it's moving straight through space. But because you and the ground beneath you are rotating, it looks like the ball is bending. To truly understand how the Coriolis effect shapes ocean currents, which occur on the open ocean, driven by a complex global wind system, let's revisit the scenario where the Earth does not rotate, where everything remains perfectly still. In this imaginary world, the atmosphere would behave very differently. Without the Earth's rotation, air would simply flow in a straight path from areas of high pressure at the poles to areas of low pressure at the equator, creating a simple, back-and-forth pattern. Cold air from the poles would rush directly toward the warmer equator, while warm air from the equator would move straight toward the poles. The result would be a predictable two-way circulation of air. In this stationary world, ocean currents would also follow a much simpler pattern, moving directly from high-pressure areas near the poles to low-pressure regions near the equator, with none of the curves or twists we see today. But the Earth is not stationary. It rotates, and this rotation adds an incredible complexity to how air and water move across the planet. The Coriolis effect bends these simple back-and-forth motions, creating the swirling, spiraling patterns of wind and ocean currents that shape weather systems, influence climates, and sustain life across the globe. As we journey through the incredible forces that shape our oceans, one truth becomes clear. Our world is full of mysteries waiting to be explored. From the depths of the sea to the farthest reaches of space, curiosity is the key that unlocks the secrets of the universe. The more we learn, the more we realize how much there is still to discover. So never stop asking questions. Never stop exploring. Let your curiosity guide you, because the wonders of our world are endless. Thank you for joining us on this adventure, and remember, stay curious.